Hello everyone and welcome back. Now in the previous video we were introduced to the 5-step method that you should use when you approach problems in mathematical modeling. And in particular we saw how to apply this approach to a very simple problem of falling goggles. Now what I would like to do is zoom out just a little bit and talk a little bit more about the components of mathematical modeling. And in particular, over the course of this lecture series, we are going to talk about two main classes of models. Now, the first class is called deterministic models. Now, deterministic models, they mean that there is no randomness. There are no random variables involved. And what it means to be a deterministic model is that the future is entirely determined by how things start right now. Okay, so think about a pendulum arm that's swinging. Well, what I can do is I can pull up the pendulum arm and I can leave that thing to swing. And if you came and did that in an hour or a year from now, and you pull it up to exactly the right spot that I pulled it up to, and you let it go, you will see exactly the same swinging motion. That's because the system is completely deterministic. There is no element of randomness involved in that. So, what this means is that typically when we are solving deterministic models, we are going to use a lot of calculus. We're going to use some linear algebra. We're going to use differential equations, so in particular, ordinary differential equations. These are the typical ways that we model deterministic systems. Now, if deterministic systems don't involve any random variables, then clearly there is a class of models that do. And those are called stochastic models. Now, stochastic models means that there is an element of randomness involved, right? So this might be something like playing a board game if you have to roll the dice, right? So just because it's my turn and I started on the go square in Monopoly, I am not going to do exactly the same thing that you did when you started on the go square. And that's because the randomness comes from whatever comes up in the dice. If we have 100 people lined up, it's possible that there are 36 different outcomes based on the values that come up with those dice. Now, of course, if deterministic models use a lot of calculus and linear algebra and ordinary differential equations, stochastic models, they use a lot of probability and statistics, right? So that randomness causes us to have to be a little bit imprecise in how we talk about things. We say, this is what should happen, this is what is expected to happen, but of course the randomness means that some very outlandish things are possible, right? So for example, if you are on the Monopoly, if you are on Go, starting a game of Monopoly, then rolling 2 dice, the highest probability thing that you can do is roll a 7. Now, I believe this would put you on a community chess square. So I say, the highest probability event that's going to come up would be landing on community chess. But 6s and 8s are also high probability rolls. So you do have a high probability of rolling on those. So you might be tempted to say something like, you are expected to roll between 5 and 10. But of course, you have the low probability of event of rolling snake eyes. You could roll 2 1s. That is entirely possible within a stochastic framework. Okay, so as we progress through the class, we're going to start with optimization and then move into dynamical systems. That's primarily going to be focused around deterministic. Now, the nice thing about deterministic is they are relatively simple to solve. They have an answer, right? The answer is 3. The answer is pi, right? There is a specific answer that people are looking for. Now, towards the end of the class, we're going to talk about stochastic models, things like Markov chains, which again have very specific answers, but they have to be asked in a different way. You have to say, what is the probability of finding someone at this square after 10 turns? Right? So you have to be careful about how you phrase these things, these questions in the 5-step method when it comes to stochastic and deterministic models. Now, those are just the kinds of models you have. The question is, what can you build into a model? Well, building a model, you might want to use something like conservation laws. So, if you have taken a physics class before, you are definitely familiar with conservation laws, right? Physics is just brimming with conservation laws. It's really how we understand a lot of the laws of reality. So conservation of momentum, for example. These are things that we sort of build into models because we know they have to be there. And they don't just have to come from physics. For example, imagine we have 10 animals in a pen and we want to sort of try and understand their movements and their behavior in the pen. Well, if we're looking at this on a short enough time scale, there's not going to be births or deaths. So the number of animals is going to be conserved. There will always be 10 animals. So that is a type of conservation that can be built into these models. Now, of course, along with conservation laws, another very, very powerful thing that we can do is we can put in constituent relations. Now, what is constituent relations? I mean, that's a very, very fancy way of saying known equations, right? So things like Newton's second law, force is equal to mass times acceleration. That's a classic, right? Physics problems use this to derive even very, very complicated models. Things like the Navier-Stokes equations just coming from force is equal to mass times acceleration. Another classic, things like Hooke's law, right? So this is related to springs and the force required to stretch a spring out. But you could have something coming from maybe chemistry, right? So this is the ideal gas law. And there have been many, many attempts that people have made to try and come up with these types of laws when trying to understand sociological relations, right? So types of responses, language death models, right? There are all kinds of these constituent relations that are hanging around. And this goes to the B of the ABCs of math modeling. Borrow, 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 right? We want to be able to draw upon what others have already done for us. Okay, so once you actually make a model, what is it that you want to do? Well, of course, you want to answer the question, right? This is the class, so you want to sit back, you want the full marks. You want to say, I want to get perfect on this problem. I want the right answer. Okay, that's great, right? That is a wonderful approach to succeeding as a student, but how do you succeed as a mathematical modeler? Well, you still have a question, and you might have a specific answer in mind, right? So, where are all of the animals in my pen after 2 hours, after 6 hours, after 6 days, right? These are quantifiable questions. But what you should really be doing once you build a mathematical model is you should be conducting numerous studies to see if things sort of make sense. They should be qualitative and quantitative studies that say, okay, even if it gives me the answer that I sort of expected. Think about my air resistance problem from the previous lecture. What happens if I tweak things a little bit, right? What happens if my ski lift is 20 meters in the air instead of 10 meters? What if it's only 5 meters, right? Do things still make sense, right? And does that kind of robustness, that kind of tweaking still make sense in my model? Now, the other thing that you should aim for is to have your parameter values. So these are your sort of constants that you are taking in your model. It might be your C and your alpha from the previous example. It might even just be the acceleration due to gravity. You want to be able to find these things either in the literature or through experiments. You want to know what those values are, right? Because think about what I did in the previous lecture. I said, I don't know what the air resistance is actually for my experiment, so I'm going to do things really generally, and so therefore I can't really answer the problem anymore. I can give you an answer in terms of C, but I don't know what C is. Well, that doesn't answer the question for me, so of course I need to be able to pull back and ask myself, what is C? Did somebody measure it? Probably. Or is there a way to measure it? Then get out there and get it. Okay, now the last thing and the most important thing is units. Okay, unit analysis is one of the most cumbersome and most frustrating thing that you can do in a physics class. And we in mathematics absolutely hate units. We try our very best to get rid of units through a process that is referred to as non-dimensionalization. So before I get to the non-dimensionalization process, I want to talk about how units are a good way to know if you put together the model correctly, right? So let me give you a little example. So let's look at this example. Imagine I give you an ordinary differential equation. I said, I've got this. dx by dt, so the derivative of x with respect to time, is equal to a, some constant, times the position, x. Okay, well, here's what we know. Okay, so since I am clearly looking at knowns and unknowns here, x is going to be measured in meters, for example. So that's good. Now, the derivative is a rate, and so it is going to be meters per unit time. In my case, let's imagine it's seconds. So time is measured in seconds. So this is meters per second, because time is measured in seconds. Then the question is, what are the units of A? What are the units of this constant A, right? So again, if I go back to what I just said, I want to figure out what these constants are because I want to be able to give definite answers. But clearly, if I give A in newtons, for example, or kilometers, is that going to be consistent, right? Does that even make sense? Do I have to do some conversions to the right units? Well, if we look at these things as a sort of fractions, this is maybe m over s, right? Meters per second, which is equal to some unit times meters. Sort of rearrange all of these things, and this means that this is measured in 1 over seconds. So this is a per unit time relation, right? This is again a rate here. And what this tells you is that either if you are given A and it is not measured in 1 over s, then you have either built the model wrong or you have measured A wrong. This gives you a self-consistency check when you are going through that model building phase, right? This tells you whether or not things actually make sense, right? We cannot compare apples to oranges. We have to have this unit consistency. This is the best way, especially when it comes to physics models, to determine if you put things together in the right way. Okay, now, as I mentioned, once we get all of the units to make sense, the next task is to get rid of them. We try and get rid of as many constants as we possibly can through a process that's known as non-dimensionalization. Now I'm going to give you an example of this. Again, I'm going to use differential equations, primarily because that's my sort of favorite subject, but it's also a good way to sort of see how these things work. Okay, so let's imagine I've got a constant A times the derivative of a function plus a constant B times the original function, and then C times some function f of t. So f of t would be a forcing function in this case. X might be your position, dx dt might be your velocity, a, b, and c might be some measured constants that you put together to build this mathematical model. Okay, so let's not worry too much about the mathematical model itself. Let's think of a way, or let's discuss a way to get rid of A, B, and C. Okay, I don't want them in there. I don't want to have to talk about them because as we saw with the previous example with the falling goggles, the C really sort of muddies things up. So if we can get it out of there, we can get ourselves into a realm where we can just do the math. That's what we want. Here's what I'm going to do. I'm going to say let x equal to a constant chi, and then times, say, xc. And I'm going to let time equal to tau times tau c, okay? So what I'm going to do here is I'm going to introduce new variables. These are the tc and the xc variables. And I'm going to do it in such a way that I am going to rescale time, okay? So maybe time was originally measured in seconds. What I'm going to do is I'm going to find a new unit of time that gets rid of a bunch of these constants, okay? So these are sort of, you think of these things as sort of natural units. You're sort of scaling everything so that everything becomes one, okay? So instead of talking about 1 second in the future, maybe I talk about pi seconds in the future because that's when I was able to measure a lot of my things. Okay, well, what does this actually do? Well, okay, my derivative here, if I plug in x and t, I get chi xc divided by tau tc. Now, tau and t, these things are going to be, chi and tau are going to be variables of time. Xc and Tc are going to be what I scale time according to. So they're going to be constants. So that means that I get Xc and Tc coming out. And I get d chi, d tau. So what I would like is to have a new variable chi that is a function of tau, which is the natural time scale. And I'm going to do it by finding the right Xc and Tc's. Okay, so into the differential equation, into the ODE. When I put this into the ODE, well, I get A xc over tc, and then times d chi d tau. That is A dx dt. That's all that I've done. Substitution so far. Plus, and then I get b xc, and then times chi. All right, that's just replacing x with chi xc. All I'm doing is putting the constants together out front of these variables. And then, similarly, I get equals c f of, and now it's going to be tau tc. Okay, so this is I understand this can be a confusing process when you first learn about it. But the goal here is to get rid of all of the constants. Right now I've got a whole mess of them. But remember, I'm allowed to choose what xc and tc actually are. So first thing I'm going to do is I'm going to get rid of this. I'm going to multiply it all the way through. So I get d chi d tau. And then plus b tc over a xc chi. And now this is equal to, I get c tc over a xc. And what I'm going to do is I'm going to call this thing now capital F of tau. Okay, so what I did here, I said capital F of tau is actually the old function f of tau times tc. Okay, so nothing too fancy here. All I did is just a redefinition. Remember, this is now a function of tau. I just want it to look like a function of tau. Okay, so what was the goal? The goal was to get rid of all of the constants. So I want this equal to 1, and I want this equal to 1. That would be awesome. That's what I want to happen. So the question is, how do we do this? Well, if we are going to do this, we need, sorry, this isn't here. That's my mistake, pardon me. This is divided off from right here. So the first equation we get is b times tc over a is equal to 1. Remember, a and b are given to you. So this tells me that I need to choose tc to be a over b. A and b are given to me. And so that means that the natural time scale is measured in a over b. That's what that tells me. And it also tells me that if I choose to rescale time by a over b, then I completely get rid of all of the constants on the left-hand side of my differential equation. I now have a derivative of a function plus the original function. No multiples, no 2's, no 3's, no a's, no b's, nothing. Okay. Then the other one is c tc over axc is equal to 1. In this case, now I've already got tc, so this actually gives me c over bxc is equal to 1, which tells me that xc is equal to c over b. And what was the point? By choosing those two values, remember, I got to choose how I rescale the variables. I got to choose tc, I got to choose xc. I chose them in such a way so that my ordinary differential equation becomes the derivative of the new variable chi with respect to, tau, pardon me, plus the original function chi, and this is equal to a function tau. Isn't that so much nicer to look at? There's no a's, no b's, no c's, nothing. No tc's, no xc's. Just a derivative of a function plus the function itself is equal to another function. No 2's, no pi's, no exponentials, nothing. It's nice and simple. That is what we call non-dimensionalization in mathematics. I got rid of all of the constants by moving to these natural time and length scales. Okay, so this is all related to what's called Buckingham Pi's theorem. And it's a way of telling you how you can non-dimensionalize a system in such a way that you can get rid of as many constants as possible by moving to these sort of natural scales, just like what we did here. Okay, I know that this is a hard process, right? This takes a lot of practice, but hopefully as we progress through the class, these are the kind of things that you'll be able to do. You'll be able to distinguish what is a deterministic versus what is a stochastic model. And that means that you'll be able to distinguish how you're going to actually solve that model, what methods you're going to use. And maybe as you're building these models for yourself, you're going to start thinking about, the sort of ingredients, the components that you might want to use. So of course you want to start with conservation laws. They're some of the most important things in the entire world, and they are the most important thing to start with building a model. And then, of course, constituent relations. We have all of these equations hanging around. Of course, we want to be able to use them. Now, units give you the sort of self-check. They tell you if things actually made sense or not. Just like what we saw right here, we had to have A measured in per seconds. And if it's not measured in per seconds, then something is wrong. It's either measured incorrectly or it's measured with the wrong units, or maybe you made a mistake. And we should probably assume that we made the mistake a lot of the time in building the model. It's a nice self-consistency. As soon as you have all of the model built, get rid of as much as you can. Make it as simple and pretty to look at and easy to analyze as you possibly can. Okay, when we come back in the next lecture, we'll start talking about optimization, the first of 3 units that we will progress through in this lecture series. So I'll see you in the next lecture.